How do our planets and objects move around the sun in the solar system? Well, astrodynamics is complex, but we can simplify it with Universe Sandbox, and today we'll take a look at the very basics of astrodynamics. Hey everybody, Thomas here from my channel Astronomy. Now today I see black bars on the left and right of my video. I don't know, my camera is maybe a little bit faulty. Anyway, shouldn't bother us because we will switch to Universe Sandbox just in a second. Now, for those of you who are longer here, subscriber on my channel, you may be a coder and you know some Python stuff and you were doing also some astrodynamics with Python. But for those of you who are not into coding or would like to know more about some more scientific background like the astrodynamical part without being a coder, this video is today for you. And what we will do today is we will take a look at the solar system and we take a dedicated look at astrodynamics, especially the motion of planets and asteroids around our sun. We will manipulate some parameters for you to understand how they affect it, because all the fancy small animations people create out there is mostly like without really knowing what's going on. So I would suggest we switch directly to Universe Sandbox and get started with our home planet. Well, and there we are, Universe Sandbox with its default loaded screen. Now this application is not crashed or so, I just paused it and now we can continue it with the entire solar system, which computes the movement with around 16.5 days per second. Now we see here Mercury, we see Venus, Earth and Mars. In total, this default simulation contains around 600 objects and around 30 of them have simulated gravitational pull, especially the sun and also the larger planets and larger asteroids. Now here we see somewhere Earth floating around. So this is our orbit of Earth. And if we make an edge-on view, like the view on the so-called ecliptic plane, the apparent, or let's say the virtual plane where our planet is revolving around our sun, we see that our Earth is creating a flat line, but the others are not, because they are a little bit inclined with respect to this so-called ecliptic plane. And this is the first word, inclination. Inclination is the tilt angle between the orbit and this virtual plane. And if we scroll a little bit out, we see that, well, there are a lot of big deviations between the ecliptic plane and some objects. Now, our planets are more or less on the same plane, on this ecliptic plane. We see Neptune, Uranus, we see Earth, Mars, Venus, Saturn, more or less around the ecliptic plane. So kinda on the same thing, let's say. Now, the larger asteroids also plus minus, a little bit higher inclined. But smaller asteroids and also the objects far away, the trans-Neptunian objects, comets and so on, they are partially highly inclined. So you see them all here. And if we take an upper view, you will also notice that all our planets, I was wondering why they are so slow, but this is Saturn and Jupiter. They are all moving into one particular direction, and this is the so-called retrograde orbit. So if you take the look, let's say from the upper part of the ecliptic plane, everything is revolving around the sun anti-clockwise. This is due to momentum conservation, like let's say when our sun was formed and all the huge gas cloud and so on, that was all revolving into one direction. Then all the planets were formed and this momentum was preserved, which is in our case retrograde or anti-clockwise. And you see basically everything is moving into this direction. There are some small asteroids that have a so-called prograde orbit, maybe because of high gravitational disturbances. They were captured by a planet or had a close flyby and the orbit was changed and altered. But you have to know that these prograde orbits, they are unstable. Yeah, not because of, let's say, physical parameters or so. The universe doesn't care if it's prograde or retrograde, But if you have a lot of objects revolving into one direction and then a smaller one into the other one, it will have it will be affected by the planets, by the gravitational pull, and it will, let's say, alter its orbit within a few thousands or 10,000s of years. So theoretically, you could, for example, take Ceres, reverse its orbit and see what happens, but I think this will take some time. Maybe we do a prograde animation video in another session, because today we are learning about the basics. And I already talked about the inclination, so I just clicked here on Earth and we can extend the menu. You will not see the Earth now because my face is there. That's not a problem. There's a small icon here, so-called show object data view. So we have the Earth here on the left-hand side, and there we can also display other things like surface temperature, elevation, and so on. But we don't care about the composition or atmosphere of Earth today. We care about the motion. Now, the motion is the setting we have here on this on the right-hand side now, where we have like the distance, we have the speed of our home planet. We have also here the orbital elements, like, for example, the orbital period, the semi-major axis, and so on. Now, I would say let's go through them step by step, and I would like to take this small bar here. There we are. And I would say we start with the default ones. Now, the semi-major axis is like, now our planet is like a circle, but if we extend it to an elliptoid orbit, then let's say the larger radius is the semi-major axis. So what we can do is we can change it a little bit, the so-called eccentricity. So we skip these parameters first. The eccentricity gives us a value of, let's say, the circularity, how circular an orbit is. It's even written here a little bit, so there's some explanatory text if you hover over it. And let's say a value of perfectly 0 means it's a perfect circle. Between 0 and 1, it's an elliptic orbit. No, not an elliptic. It is an it is elliptoidic orbit. If we have a value of exactly 1, it's a parabolic orbit, so it's not bound anymore to the sun. It will have one flyby and that's gone. And values over 1 are so-called hyperbolic, and these objects are also not bound to the sun. Now we have an eccentricity of almost 0, so it is not a perfect circle, but, well, we don't see it really, so we can change the value here a little bit. Let's say we increase it a little bit. You will see we will manipulate the Earth a little bit. So we increase the value, and you see how it gets bigger and bigger and bigger, and I should stop at some point. And now here, oops, I would just want to have the sun in the center. Now here the Earth is now revolving in a larger orbit. And we see it also now with the so-called semi-major axis. Somehow, where is it? Skip there. We are the semi-major axis of 2.35 AU, which is, if you take the center here and then compute the larger radius, this is like the semi-major axis. Now, the pericenter and the apocenter are the distances, the closest and the biggest distance to the sun. So in our case here, it's 0.9 AU. So here, but the distance between this point here and the sun is almost 1 astronomical unit. So the average distance between Earth and sun now, and the larger distance is 3.72 AU. So very far away. And it's also getting kind of cold there. We can also change these parameters, but as you may think or know already, the semi-major axis and the eccentricity, they have a direct impact on the pericenter and the apocenter. So changing these values will interact with each other. So these are the, let's say, orbit shaping parameters. Now, if we go a little bit down, we see here the inclination I already mentioned. Now it's 0.006 degrees. Now you will say, hey, wait a second, I just said 0 degrees is the ecliptic plane. Yes, the ecliptic plane is called ecliptic J2000. And what does it mean? It means that our ecliptic plane is defined with the Earth parameters at the year 2000. But in the last 24 years, Earth's orbit changed already because of gravitational perturbations and so on, and it changed its inclination consequently. Now in this case, it already changed also its parameters because of this weird orbit, but yeah, we do not have 0 degrees now. Now if we increase a little bit the pace, let's go a little bit faster, so our Earth is revolving faster, we can increase the inclination. You will see how it goes up. And there we are, 30 degrees. Now it has a very inclined orbit around the sun. So you see it also gets faster, closer to the sun, and slower beyond. This is one of so-called Keplerian laws. And the funny thing is now, if we increase the inclination to 90 degrees, we have something called a polar orbit. Now this is almost 90 degrees. This is a polar orbit. And if we are now going way more than 90 degrees, we get the prograde orbit. As I told you in the beginning, that this is not really present in the solar system for the major objects. They are all moving into one direction. Now you see Earth moving into the other direction. And as I said, play around with this. Put, for example, instead of Earth, Jupiter or so, and see for both directions how stable the solar system is. Very well. We can slow down the things a little bit. The argument of pericenter and the longitude of ascending node. What does it mean? Now, of course, our ecliptic plane, our coordinate system, is somehow referred or has there's a reference frame that has to be defined somehow, right? So the ecliptic plane is like our XY axis. And the x-axis shows to the so-called vernal equinox point. So the direction from Earth to Sun at when there was the vernal equinox in the year 2000. So 20th or 29th of March. And the y-axis or the z-axis is consequently, let's say, the ecliptic north pole. And then the y-axis with the right-hand rule is then determined. So all the axes are perpendicular. And based on this reference frame, we can then, for example, rotate the pericenter. So the angle between the vernal reference point, let's say, and our closest point to the sun is defined with the argument of pericenter. So we can rotate it a little bit. And as you see, we can do it in real time. So if we have like here 0 degrees, or 360, it doesn't matter. We have like, where is Earth? There it is. It's like the direction where the Earth was looking to the sun at the vernal equinox point. And the same thing applies also for the longitude of ascending node. What does that mean? Well, we have like here, we should change the inclination again. It's getting very chaotic. And I would like to change the pericenter a little bit to make it more apparent. There we are. Now we take a look, the edge on view now on the ecliptic plane. And we see now our highly inclined Earth, who is crossing the ecliptic plane twice. One point, we just missed it when it's coming from the, let's say, upper part to the southern part, penetrating the plane, and now going up again. And this going up means it is ascending, and crossing this point is like the so-called longitude of ascending node. So the longitude is like the degrees, the angle between the vernal equinox point and the point where Earth was penetrating the ecliptic plane, but from the south to the north part, like now. Good. So if we change this value, the orbit has to rotate somehow around its, let's say, south-north axis in a way. So let's see if this happens, and we see it does happen. It's nice that we already get a projection of the orbit, and I would like to move a little bit the camera angle so you get an understanding how it looks like, and you see that the coordinate where the Earth is getting through the ecliptic plane is this is Jupiter, is changing. Yeah, so I think it's easier if you do it now here from the top view. Here's the ascending node. Let's have a look again. We can rotate it and change the values accordingly. That's the pericenter longitude. Yeah. The last one, the true anomaly, it's not really important for the orbit itself. The true anomaly indicates it's like an angle to the Earth. So it gives us for a certain date time the position of our home planet on this orbit. Though this is also the reason why the true anomaly is changing all the time, because Earth is rotating, and if I freeze the time, the true anomaly will stop as well. Now these are all the orbital elements. Now mean anomaly is also another angle, but yeah, I don't want to put too many equations here in this series, so let's take it as it is. So this is like the most important things. Now, what is resulting from that is, of course, the distance to our sun, and of course the orbital speed. The orbital speed highly depends on the orbital parameters we just set. So if I reset everything, you will see that with the settings we have now, 1 AU, very circular orbit, and so on, we see that around 30 kilometers a second is like the average pace of Earth revolving around our home planet. And you know what? I would suggest let's do this. We are restarting everything here. Everything is set and is back to normal values. Now we can click here on the speed, for example. We take the graph and then we can track it, and we wait for a full year maybe. So it is increasing a little bit over time. Why is it increasing? Because it's getting closer to the sun, and then it's also getting away from the sun a little bit. And now take a look on the bottom left at the time and the pace here. A higher speed means it's closer to the sun when it's a little bit an elliptic orbit. So it's closer. Yeah, so high values means closer to the sun. Slower values means it's far away. And now if you check here, for example, the lowest value now, it's around July. So it's almost now. If you watch the video during now in July or August, which means that in the Northern Hemisphere we have summer, but although we have summer, the Earth is far away from the sun than during winter. Sounds pretty crazy, but of course, some of you may already know it's not only about the distance between the sun and the Earth. This changes by a few, let's say, kilometers, but it's been more than kilometers. It's also because of the tilt angle of our Earth, right? So the tilt angle stays the same, and we are rotating around the sun, so that in the summer we have more light illumination in the Northern Hemisphere, and in the winter we have less. So this is like the main drive for our seasons in the Northern Hemisphere. So the distance really doesn't matter here in this case. We can verify this by going here, and on the x-axis we have, we leave the time, but on the y-axis we can put the distance, and then we will see the effect that we have here, the distance going up and going down. Now again, we have here now December. We have our smallest distance, less than 1 AU. Now, and the distance increases, and then around July, it has a maximum distance, like around more or less now, and it's going back. So this is all about the values. Now, I hope you learned something today about these astrodynamical properties, some smaller deep dive here. Play around a little bit with the values, compare, for example, the Earth with also the other planets to get an understanding how these things work. You can also check online like the distribution of the inclination and the orbital elements for the asteroids. There are some interesting facts that we cannot cover here with Universe Sandbox now, but because they can be seen in the statistics of 10,000s of asteroids. But yeah, this is just details. We have also orbital elements, not only with respect to the sun as a center, but also with respect to Jupiter, for example, or other planets, because Jupiter has also its moons. I don't know if Jupiter has its moons here in this simulation. Well, unfortunately not. But our home planet has, of course, a moon. It's also not simulated here. But of course, if we have a reference frame like the sun, then our moon appears like also on an orbit around the Earth, right? It has also some kind of orbital elements. But if we take the Earth as a center, then we can also compute the orbital elements of our moon with respect to our home planet and so on. So orbital elements are not fixed to the sun. They can be computed with respect to any object, to the Earth, to Venus, to Mars, anything. And this is maybe something for another video to cover. So thanks for watching. I hope you learned something, and until next time.